velocity and displacement equation. Displacement was done, velocity and acceleration. So velocity as a function of time, like when you have time, the equation is minus omega a sine omega t plus phi naught. As a function of position, it is omega under root a square minus x square. Acceleration is minus omega a cos omega t plus phi naught as a function of time. And when you have acceleration as a function of position, it is minus omega square x. So this is what we in that this we discussed. Yeah. Displacement versus time, velocity versus time, acceleration versus time. This we had to plot. So x is equal to a cos omega t, v is equal to minus omega a sine omega t, and a is minus omega square a cos omega t, right? These are the equations which we obtained. So look, for cos, the graph always starts from here. For sine, it will start from origin. For cos, it will start from here. So look, this is how it will look. It will appear for t by 2, t by 4, then again 3 by 2, like this the wave will go. And for velocity, this will be from 0, minus omega a, then plus omega a, then minus omega a, plus omega a, like this. And for the acceleration, again, it is minus omega a square, but it has cos, so it will be from here. So only the velocities graph will start directly from origin. Rest of it will start midway after 90 degree. So this graph you should know. Please write down this graph. Then I'll start with energy. When this energies equations are left, then two systems you have, spring and pendulum. Let us complete this chapter today. Please write this. Shaima, we have started with this only. This is the question part. Take the screenshot of this, and that is the graph part. Done, all of you?
No. Can you scroll up?
All of you have completed? Ali, Jesleen, Shaima, can we move forward? Okay, coming to energies in SHM. Energy, you have the kinetic energy and the potential energy. I'll start first with the kinetic. So you know what, whichever energy is due to change in motion of the body, it is called as kinetic energy. And the formula that we have been using is half mv squared. Now, in order to convert this, see, velocity's equation is minus omega a sine omega t plus phi. If we put it, so kinetic energy will become this will be the equation as a function of time, because this is the function of time. So this will become the equation as a function of time. See, this we already discussed that this is the velocity as a function of time. So this is the kinetic energy as the function of time. We have done nothing. We have just put the value of velocity in our usual equation. What if I want to get the same thing with the equation of position? So I'll take the equation of position. V is omega under root a square minus x square. So see, a square minus x square to the power half, and I am squaring it. So root will go and omega square will be there. So kinetic energy will become half m omega square a square minus x square, right? We have squared this up. Uh, this square won't be there. We have cancelled the root. This is it. That will be left. So is when we are talking about this equation, this is as a function of position. This is the function of position. And this is the function of time. For kinetic energy, you need to remember these. Okay, one more thing. If I write about the extreme and mean position, okay, if I write about the extreme and mean position. So see, this will be, let's say this is the mean position. So at mean position, x is equal to 0. Right, so your kinetic energy will be equal to half m omega square a square. That's it. Why? Because this is 0. And if we are talking about the extreme position, so X will be equal to A. So kinetic energy is equal to 0. That is, it will have the minimum value here. And half m omega square A square, this is the maximum value. Okay, maximum value at the mean position, minimum value at the extreme position. Okay, potential energy, I'll start first write about the kinetic energy. So kinetic energy is position equation, function equation, and mean and extreme. This is what you See, now coming to potential energy. So in work energy and power, we have seen that the formula of potential energy is half kx square. And x is a cos omega t plus phi naught, the displacements equation, right? So you will become half k a square means, sorry, x square, that is a square cos square plus phi naught, right? So this is what? This is a function of time, this equation. Now see, if you have half k x square, this is already a function of position, right? This equation is already a function of position. So this is what? This is the function of time. This is function of position. In this, we will get again two cases. One will be the mean, other will be the extreme, okay? Which one is this? This is, let's say this is the mean position. So what have we discussed? That in mean position, x is equal to 0 at mean position. So potential energy will be equal to 0. Then second, we have the extreme position. So to A. So potential energy will be equal to half k a square. Now see, this will be what? This will be the maximum value. Square is written as k by m. So u can be written as half m omega square a square. So this also can be applied. Now see, if we talk about the total energy, look here class, when you take the sum of kinetic and potential, you are left with half m omega square a square minus x square plus half kx square. So when you open up the bracket, m omega square is k only. So half kx square will be cancelled. And you will be left with half ka square. So the graph of kinetic energy and potential and total energy is represented as this. See, this is showing the extreme points. This is showing the mean point. So this is the kinetic energy one, where at the extremes it is 0 and highest at the mean, and opposite is for potential. See, at the mean it has the highest, and this is, and total energy is just independent of mean and extreme because there is no x in its value. So it is same for mean, same for extreme. X determines your mean or extreme. Right now there is no x, so it will be half ka square only. Write it, then we'll see a question based on this. Write it from here, potential energy. See, this question says a body executes SHM of time period 8 seconds. If its mass is 0.1 kg, velocity after 1 second is through its mean position B 4 meter per second. So velocity, this is saying that passes through its mean position is 4 meter per second. We have to find its kinetic energy. Okay, so what is there? A body executes SHM of time period 8 seconds. If its mass is given, velocity is given, and time is given. And what is the position? Passes through its mean position. So what all things we have? We have to find out kinetic energy, potential, and total. So time is 8 seconds. At t is equal to 1 second, we have the velocity as 4 meter per second. And mass is also there, 0.1 kg. Amplitude we don't know. So see, velocity is dx over dt. That is a omega cos omega t, right? Because x is equal to a sine omega t at mean position. We have to take mean position. No? It has mentioned in the question. So this will be a sine omega t. Remember, sine for mean and cos for extreme. So we differentiated this and we got velocity because we don't know. This is saying velocity when it passes through its mean position. We don't know velocity at the mean position or extreme position. So velocity is 4. Let's see what is the amplitude. Omega. So see, omega is 2 pi by t. So we can write this as 2 pi by 8. Cos 2 pi by 8. Time is given as 1 seconds. Because we know x is equal to a or anything has not been mentioned. So if we solve this, this will be 4a into pi by 4 into this will be 1 by root 2. So a will be equal to 16 root 2 by pi. What is this? This is the amplitude. We have obtained the amplitude from this. Okay, so 16 root 2 by pi, this is the amplitude that we have obtained. Now we have to find out various things. Total energy. If we find out total energy, then kinetic and potential will be very easy to calculate. I'll tell you a relationship also between them. Total energy is half k a square. So it will be half m omega square a square because k is equal to m omega square, right? So look, total energy will be half, mass is 0.1, omega is pi by 4, right? 2 pi by 8, so this will be pi by 4 whole square. And amplitude we have got 16 root 2 by pi whole square. So when you will solve this, you will get this as 1.6 joule. The total energy will come out to be 1.6 joule. Now for the rest of it, no, see a relation that half of the total energy. Okay, kinetic energy is half of total energy. So kinetic energy will be 0.8 joules. And potential, when we're talking about the potential energy, see, kinetic energy plus potential energy plus potential we don't know. This is 1.6. So potential energy will also be 0.8 joules. It's just that this becomes negative. Okay, total energy, total, see, when we are talking about a relation, I'll tell you. Total energy is there, okay? You have kinetic energy present and you have potential energy present. So kinetic energy and total energy, they are just negative of each other. So when you write, you can use the rest of the relations also. So in total energy, this is simply negative of kinetic energy. You can put it like this. And when you have the total energy in terms of potential, when you have the total energy in terms of the potential, so this becomes potential energy by 2. I've written P. So see, this becomes total energy will become whatever is the potential energy by 2. Okay, I've interchanged it. This will be kinetic. This will be potential, total energy. So it will be double of it. Wait. If we are talking about the kinetic energy, so we'll just put a negative sign. That will give us our answer. So kinetic energy, it will be simply negative of the total energy minus the total energy. So it will be minus 1.6. That's it. If total energy is 1.6, this will be minus 1.6. And when this is 1.6, see potential energy, simply use this relation to calculate. The potential energy will be twice of it. So potential energy will be double the total energy. So potential energy will be 3 joules. These using these two, this is the part and potential. Okay, so this is how you can calculate. Okay, I'll repeat this. See, mass is given, velocity through its mean position at any portion it is given. Now look, we calculated the amplitude first because we didn't know the amplitude. So what we did, this was the equation for mean position. We differentiated it to calculate the velocity's equation. This was the equation of velocity, A omega cos omega t. So we put all the values. A, the velocity's value, A as it is, omega cos omega t. Rest of the things were given in the question. We solved this and we obtained this amplitude. First, tell me, till here, is it clear to all? Amplitude part?
Yes, ma'am.
Okay. Once we had the amplitude, we calculated total energy, half Ka square. We obtained 1.6 joules. So put it at it as minus 1.6. And total energy is half of potential energy. So potential will be double. So we took it as 2 into 1.6. Now is it clear? Now this whole question is clear to all of you?
Yes, ma'am.
Write it.
Ma'am, can you scroll up for a second? Ma'am, a bit more.
The question part.
No, ma'am. Done, ma'am.
Okay, class, now two systems are there in your syllabus. Spring mass system and simple pendulum system. So first, let us see the spring mass system. Two arrangements like this. See, a horizontal spring can be there. This is the spring with this mass. All right, just wait. Is it still lagging? Okay, wait for 2 minutes. Class, is it better now? Yes, Ali, Jesleen, Shaima.
Yes,
Okay.
sir.
Okay. So I was saying that we have two systems in your syllabus. You have two systems. One is spring mass and other is simple pendulum. So when we're talking about oscillation of a loaded spring, two kinds of arrangements of springs are possible. One is the horizontal one. This is how this horizontal one will be and what will be its mechanism. There would be a central mean position. Let's say this is x equal to 0. And this separation is x, which is equal to a, basically the amplitude. X is equal to a, the amplitude from the maximum separation from the mean position. So here, through an external force, we'll be pulling it, and a restoring force will be developing, which will lead the spring back to its original position. Similarly, there is arrangement of the horizontal spring also, vertical spring also. Vertical spring means same thing. Like this, the spring is put. So again, it will also be having its mean position and it will extend to its extreme. So this is the mean and it is extending to its extreme position. So few formula are there which you need to know. See, restoring force is equal to minus kx because it's the equation of SHM. Now, what all things are there? I told you that omega is equal to under root k by m. We have been using this also. So this can also be applied here. What is k? K should be known to you. This k is basically the spring factor. This is the spring factor. And in this system means spring factor is said not just for spring, for all the systems that are present. This constant is called the spring factor. But when we are specifically talking about the spring mass system, then in that case, we will call this as the spring constant. Understood? See, spring factor is for all the systems that are present. You have U-tube, you have Earth's tunnel, you have spring mass system, you have pendulum, all the constants that are present. We say this constant is called as a spring factor. Spring is not just related to the term or the terminology related to the device spring. No, this is the spring factor. Now, different values of spring factors are there for different systems that are present. So here in this system, Yeah, this is also a force factor, right? So 2 pi by t is equal to under root k by m. So yeah, I was saying that in this system, when we're talking about specifically the spring mass system, then it is called a spring constant. So there's a difference between the spring constant and a spring factor. Now 2 pi by t is equal to under root k by m. This is the formula. So from here you have the formula of time period as 2 pi under root m by k. 2 pi under root m by k. This is the formula for the time period. Similarly, time period and frequency are inversely proportional to each other. They are just reciprocal to each other. So this will change. This k will go up 2 pi and this root m will come down. So this is the formula of frequency. So frequency, time period, omega, this should be clear to you in case of the spring mass system. So oscillation of a loaded spring is there. So let's see a question also. First, write down this part. Done.
Yes, ma'am.
Okay, let's see the numerical based on this. So a 5 kg collar is attached to a spring. Spring constant is given as 500 Newton per meter. Okay, it slides without friction on a horizontal road. The collar is displaced from its equilibrium position by 10 centimeters and released. So 5 kg collar is there and it is attached to a, so spring constant is given. What all things we have? Mass is given as 5 kg. The spring constant is given as 500 Newton per meter. And the displacement from the mean position, x is given as 10 centimeters. So I'm writing it as 0.1 meters because everything is there in the SI unit only. Right, so we have to find out the time period. So time periods formula, we have seen the first part, time periods formula is 2 pi under root m by k, right? That is the formula. So we'll put it 2 pi, mass is 5 by 500. That becomes 1 by 100, which is 2 pi by 10. So time is equal to pi by 5 seconds. Coming to the second part, this says maximum speed. Okay, class. So for the speed, now position is given. So we should use this equation under root a square minus x square for the velocity. So see, right now what it is saying, maximum speed. So it is displaced from its mean position by this much distance, right? This is displaced from its mean position. So at mean position, what happens? Your x becomes 0, right? At mean, we are talking about the mean position. Remember, x has two values. X is equal to 0 at the mean position and x equal to a means complete amplitude at the extreme position. So it has started from its mean position. Means your x is gone. V is left, that is omega a, which is the maximum value. So omega can be written as 2 pi by t and amplitude is there. So it will be 2 pi. Time period is pi by 5. Amplitude is 0.1. So this will be 1 only. So velocity will be 1 meter per second. Last part was acceleration. Yeah, maximum acceleration. So same thing when it is saying a maximum speed, maximum, why did we take all of these? Because it is clearly saying maximum speed, maximum acceleration. Class, if only speed was given, then it would be difficult for us to understand because it is saying it is displaced from its mean position. Mean position is here, it is displaced now. So it becomes a little difficult to identify whether it's exactly at the mean position or not. Then we had to calculate x also because it has said that maximum speed and maximum acceleration. So you can directly also use the formula like this: a max is equal to minus omega square a, because these are standard formula. You can use it directly also. So it will be minus omega square will be 100 and this is 1.1. So it will be minus 10 meter per second squared. So your maximum this is maximum speed, maximum acceleration will be 1 meter per second squared. Clear? Maximum speed, maximum velocity, and you have this as pi by 5. So we have written it as 100. We have converted. Yeah. Okay. Question also you have not written. No? Write the question, write the solution. Here at the end, this is saying constant and this is horizontal road. One last topic is left. That is the pendulum one, time period of a pendulum. Done?
Done, ma'am.
See, class, we've already studied many things in the laws of motion already. So the lift problems are there in your laws of motion. But see, simple pendulum is a part of your SHM. So since it's a part of your SHM, you can get the question related to it. Okay, so simple pendulum is present. Now, one simple formula of time period that I told you earlier also, if you remember when we were discussing the thermal properties of matter, that time we saw the time period of a simple pendulum was given. Time period was 2 pi under root L by G. So remember I told you that if there is thermal expansion, linear expansion is there, so length increases, so your time can increase. T is equal to 2 pi under root L by G. Time and length, they are directly proportional to each other from here. So if your length increases, the time can increase. So if the temperature rises, length can rise, temperature time period can rise. Okay, and the opposite, if it is decreasing, the length can decrease and the time period can decrease. So T is equal to 2 pi root L by G. This is the formula for the simple pendulum. We'll see this, and this is there from your units and dimensions also, where you have to derive the formula. So it's a very important formula. Now we'll see a question that is similar to your laws of motion, because it's a pendulum's involvement is there. So we will practice one question from it, then I'll tell you the derivation. Just one thing, class. Here, remember, the effective acceleration due to gravity will not be just the acceleration due to gravity. Rather, the acceleration of the lift will also be taken into account. Means if the acceleration of the lift is in opposite direction, and acceleration due to gravity's direction is always fixed. Acceleration due to gravity will always act downwards. So your net gravity will become G minus A. If both are in the same direction, it will become G plus A. So like this, you have various modifications of the questions. Quickly write the question. I'll discuss the solution. First, write all the parts. 3 parts are there. Written the question, all of you? Look here, look at the first part. It is saying a simple pendulum is placed in a, okay, you couldn't see this, na? In a box. And this is saying calculate the when the lift is accelerating up. So for the first part, the lift is accelerating vertically up, means lift's acceleration is up. But gravitational acceleration due to gravity will always be acting downwards. So even if you have the pendulum, the mass, the bob is attached, and this is the length of the pendulum. So in the first part, see, acceleration due to gravity is acting downwards. Acceleration of the body, that is the lift, that is upwards. So both are in opposite direction. So take sign convention. In such cases, take sign convention. Take one side as positive, take other as negative. Okay. Here, two things are occurring. Acceleration is up, acceleration due to gravity down. Take one thing as positive, take the other as negative. Let's say, let's take the up direction as negative. Let's take downwards as positive. So when we are taking the net resultant of the acceleration, the effective or the net acceleration due to gravity will be g minus, because this is an opposite direction. Angle is 180 degree, both are vector quantities. So g minus. Now, what is the acceleration's sign convention that we took? It is negative. So g minus minus a. So minus minus becomes plus. So it is g plus a. So when you are calculating, the time period will be 2 pi under root. Instead of L by G, it will be L by G plus A. So see how the SHM's chapter, oscillations chapter, is connected to your chapter 4th of the first book. That is laws of motion. So you won't get independent questions in the exam. The questions will be mixed from the first book, the second book. The thermal properties will also come into action. So relate all the chapters and then study. Now, what is the second part saying? Second part is saying accelerating vertically down, means lift is also going down and acceleration due to gravity always goes down. So this both, we'll take both of them as positive. Now effective will be g minus a. So t is equal to 2 pi under root L by g minus a. Okay. Now coming to the third part, when the lift is freely falling, means the acceleration, what will be the acceleration of the lift class in the third part? If it's a free fall, what answer? Third part, what should be the acceleration of the lift? Yes, Shaima, say.
G.
G. Correct. It's right. Because it is falling freely, means now the body is completely under the control of gravitational forces. So acceleration will also be due to gravity. That is the acceleration due to gravity. So lift is now freely falling. So you don't have to take the acceleration different. So what will happen? Yes, Jesslyn, you tell me. If lift is falling with the same acceleration, g, and acceleration due to gravity is already g. Now, what is the g effective value that I should take? Yes, Jesslyn, you try. Okay, Shaima has answered. Yes, Ali and Jesslyn, both of you answer. What should be the effective? Okay, why are you people saying 2g? See, in this is a similar part to the second, no? Both are in the same direction. Freely falling means lift is also going down. This is also going down. Okay, even if we take both of them as positive, g minus, this is g, it will be 0. So if this is 0, what should be the time period? 1 by 0. 1 by 0 is infinity. So time period will become infinite if the lift also starts falling with the same value of acceleration due to gravity. Okay, so because it is in the denominator, so it would be reciprocal of it, right? So this is the third part. Now, coming to the last part, accelerating horizontally. Now, this accelerating horizontally is also not tough. This is saying lift is going like this, but we know that acceleration due to gravity always goes, it will always go downwards, right? This will always be going downwards. So angle between them is 90°. Now, when you are calculating the effective value, it will apply your vectors. All these quantities are vectors. Apply your vectors. Cos 90 is 0. So this will be under root g square plus a square, correct? So t will be equal to 2 pi L by root g square plus a square. This whole root. Tell me, are all the four parts clear to all of you? Ali Mohammed, Jesleen, clear? All the parts are clear? Okay. Write down the solution. Then one small topic is left. From this only, the derivation of the time period, how we have obtained this time period. So that I'll see, and this chapter is almost over. Please write this quickly. Class done? No, not by the hypotenuse. See, these are two vectors making an angle of 90 degree. You apply the parallelogram law, a square plus b square plus 2ab cos theta. Cos 90 is 0. So under root a square plus b square. One is downwards, other is acting horizontally. Clear?
Yes, ma'am.
Okay, have you all completed?
Yes, ma'am.
Yes, ma'am. Completed.
Okay. So there's a small portion is there that can come in the exam, that is there in your syllabus this year too. So effective length of the pendulum is, let's say, delta, and the pendulum is swinging from the mean position to the extreme position in between. The pendulum is swinging. Now there's a point at the separation of the length of the arc, let's say, is x, and I have taken this point, and the downwards force that will be, or all the forces that are acting. First, let us consider all the forces that are acting. So downwards is mg. So let's say this angle is some theta, angle along the vertical, right? This is an angle along the vertical. So let's say this is some angle theta. Why? Because this will be theta. This is the actual angle theta. Okay, so this will also be theta. Now if we resolve, this component will become mg cos theta, and the tangential component to it becomes mg sin theta when you do the resolution of vectors. Correct. So here the external force is allowing the pendulum to reach the extreme point, and the restoring force will try to bring it back towards the mean position. And this is the general effective length mean. See, if the pendulum is situated here and the angle is increasing, so it appears that the length of the pendulum might increase, right? So because of that, I have taken this as the effective length. Effective length means it's the length of the pendulum, nothing else. It's the length of the pendulum. So yeah, m is the mass of the bob, L is the effective length, theta is the angle along the vertical, means this one. Okay, the angle that the pendulum makes, it sweeps along the vertical pathway when it is swinging in between the mean position and the extreme position, right? And the restoring force, what it is doing, it is trying to bring it back. So out of all the, we have one more thing, class, tension will also act. It's a string, so tension will also act. Now you all tell me, out of all the forces which are visible to you, including the resoluted forces, right? All the forces that I have resolved. So the resolved forces and all the forces that are present intact, which one do you think is likely to bring the bob back to the mean position? Which one? Out of all this, which one is likely to bring the bob back to the towards mean position?
mg sin theta.
Right, very good, Shaima. Mg sin theta. So here the restoring force is minus mg sin theta. Why minus? I've told you earlier also that it is directed towards the mean position. Correct. Now, very small angle, I've told you, for the small angle approximations, we take sine theta or tan theta almost equal to theta. Now, if you look at this arc that has been formed, this is theta. This displacement now is the length of this arc, and let's say the radius is there. Now radius will also be the length of the pendulum, right? The length of the pendulum. So here the force that is acting is minus mg theta, right? Force that is acting is minus mg theta. So x becomes equal to, see, you know the formula, the angle is the length of arc, the length of arc by the radius. So we will take this as x by, or we take x as L theta, right? So x becomes equal to L theta. So from the arc, so from here theta is equal to x by L. So what is the force equal to? Force is equal to minus mg, more than the translatory force. This is the rotatory force. Torque is minus f theta, right? So minus k theta. torque is basically minus k theta. So this is actually your rotating force only, torque, because we're talking about the angular displacement. I've just written it as the force so that you are able to relate it. So minus mg by L, theta is x by L, right? Mg by L and theta is x by L. No, so L I have already written. So this will be mg into. Now look here. If I rearrange some terms, okay, F is equal to what should be there? Your force is directly proportional to minus x. Actually, your torque is directly proportional to minus x. And since force is involved, so your acceleration will also be proportional to minus x. Mainly, your equation of SHM is F is equal to minus kx and torque becomes minus k theta. So even if you're taking it as torque also, because rightly it has to be torque, that's why we have taken this, right? If we are taking this mg sine theta, so sine theta has been written as theta. So from this step only you can figure that torque is directly proportional to minus theta. But from this step we have written mg as theta, mg theta. So on resolution, more than this, see what's the constant coming. We know omega square is equal to k by m. What is the constant here? Constant is mg by L. Now, omega is equal to k by m. What is time periods formula? From this 2 pi under root m by k. Let's put this. We have the value of k. How have we got the value of k? Because this is similar. Look, this value is coming similar. F is equal to minus kx. So directly we have our value of k. Now look, if you put it here in this formula of time period, t becomes equal to 2 pi under root m. K will be mg, L will go up, gets cancelled. So your time period is equal to 2 pi under root L by g. This is the formula of the time period of a simple pendulum. So regarding the questions, you already know these kinds of questions only will be coming, these effective, which will be combined with the laws of motion. So this derivation is there in your syllabus and it can come. Tell me class, this chapter is clear to you? Any portion, any part that you find weak? Is it clear to all? Jasleen, Shaima, Ali?
Yes, ma'am.
Okay, write it.
Ma'am, can you scroll up for a second? Done, ma'am. Ma'am, can you explain the tau part?
Which one, Shaima?
The torque part.
This one, the figure.
The torque part.
Acha, torque. Okay. Done. Yes, Shaima, I will. First just copy it. I'll explain it. Ali has done. And till here, all of you have written? Rest of you also? Jesslyn done? Okay, and what about Ali? Okay, okay. Then rest of you can leave. Shaima, I'll just explain you. Because time is already up. Tomorrow we'll start with waves. Okay, last chapter is left. Waves we'll start with. Yeah, Shaima. See, here what exactly is torque? Torque is the rotating force, right? Rotating force, the force that acts, it's just an analog or rotational analog of your linear force. That is torque. We know this, right? Now see, when basically F is equal to mg theta, how are we getting it? F is equal to minus mg sine theta. You only told me that this is the restoring force, because out of all the forces that are present, mg sine theta is the force which is bringing it towards the mean position back. Right. Now, we know the angle will be very less. A pendulum, how much will it be producing the amplitude? So angle will be very less. So we can say sine theta is almost equal to theta. And we can write this, instead of this sine theta, we can write this as theta. Now forget torque. Torque is not very important here. Just remember, F is equal to minus mg theta. Now, F is equal to minus mg theta. Theta is there. Now we replace this theta by x by L using our normal arc and the length and the radius relationship. When you put it here, if you put it like this, can you see F is equal to minus some constant x is coming? It means this constant is what? Mg by L is what? Your spring constant. So once you have the value of K with you, now we have the value of K. K is mg by L. We can put it here, get omega. We can put it here, get time period. When we put it in time period, we get 2 pi under root L.